In the previous video, we measured our system's dead time and time constant and built our simulation by inserting a PID instruction and setting up the process simulator. We left the simulation running but not doing anything because the PID coefficients were all 0. Now remember, the simulator only runs for 60 minutes at a time. Why? Because it's a real PLC that does everything a hardware do more PLC does, and it can even communicate via the PC serial port. Since Do More Designer is free, the time limit just prevents folks from using it as a free PLC. So toggling it off and back on again gives us another hour to play. Let's do exactly what we did on the real hardware in the previous video. To run AutoTune, we need to get the enclosure up to the 110 degrees we want to maintain, which I'll mark with the set point. The set point isn't doing anything, we're just using it to show the temperature we're trying to get to. We know it takes around 37% heater power on the real system to do that, so let's force the simulated PID output to 37% and see what happens. Now remember, we're overriding the PID instruction to give us manual control of the PID output right now. There was a few second delay and the temperature started to rise, just like the real hardware. Cool. This is going to take a while, so I'll fast forward the video. Okay, that took a little over 20 minutes, and look at that. Exactly the kind of response we expected, and it's similar to our real system. Cool. Let's toggle the simulator to stop and back to run to buy us another hour of simulator playtime. Now the problem is, restarting the simulator reset the process variable, and we don't want to wait another hour to get it back to 110 degrees. So let me show you a trick. To get the simulated enclosure back to 110 degrees quickly, I'm just going to minimize the dead time and the time constant. The process variable quickly gets back up to 110 degrees, and then we restore the dead time and the time constant. And just like that, we saved ourselves an hour of waiting for the simulated oven to heat up again. How about that? Okay, we're back, and the process variable is just under 110 degrees, so we're perfectly positioned to start AutoTune. Hit AutoTune. These options are all fine, so just do it. Let's rescale this so it's easier to see the AutoTune results, and I'll fast forward it so we don't have to wait around a couple minutes. And look at that. There's the typical AutoTune cycle we expect to see for a closed-loop AutoTune. And here are the resulting coefficients. Remember, these are for an ideal system. Will they be the same as the ones we got on a real system? Well, no, of course not. They're quite a bit different than these coefficients that we got from that last tuning we did on the real hardware, aren't they? The AutoTune cycle looks pretty similar though, which tells us we did a good job of measuring the dead time and the time constant. But will these coefficients work? Now before we find out, we can go back to whatever the ladder logic says to do, or we can drop directly into either override mode. Let's drop back into the ladder logic, which has the PID instruction in auto mode at all times. Notice that the coefficients automatically got updated in the PLC when we exited the dialog. But we haven't put them in our ladder code yet, have we? So, before we forget, let's bring up the dedicated first scan task and add those coefficients to a PID init instruction, so now those values will be properly loaded into the PID instruction when we start up the PLC. Accept, save, right to the PLC. Okay, time to find out if AutoTune worked on our simulated system. Let's move the set point up to 115 degrees. Fast forward, and sure enough, PID automatically adjusted the heater power to get us there as fast and as efficient as possible. Drop down to 100 degrees. Let me readjust the scaling so we can see that better. And again, PID automatically adjusted the heater power to get to that temperature quickly and efficiently. And let's get back to 110 degrees. Wow, that looks perfect. A little overshoot and then it settles right out. That's exactly what I like to see. Let's add some noise to our simulation. On the PLC simulator, click on Sim, then set up the process simulator. After playing around a bit, I found this gave me noise similar to our real hardware. Ah, look, the process variable got a lot noisier, didn't it? I'll zoom in a little bit so we have a better view of that. Now we know from the previous video that AutoTune struggles with noisy signals. Let's see how it deals with this one. AutoTune, let her rip. Well, guess what? AutoTune finished way too fast, didn't it? Just like it did in the previous video. And we didn't get the 3 closed-loop AutoTune cycles we expect, did we? In the previous video, we filtered the process variable to fix that. In this video, we're going to keep the noisy signal, and instead, we're just going to increase the deadband. Now remember, closed-loop AutoTune increases the output until the process variable crosses the set point. Then it turns the output off and waits for the process variable to cross the set point in the other direction, and it repeats that 3 times. The problem is, AutoTune sees the noise crossing and it thinks it's done. The deadband says wait until the process variable crosses this set point plus a little bit on the way up, and wait until it crosses this set point plus a little bit on the way down. This is the deadband. It's basically a hysteresis thing, and it's just a percentage of the set point. For our demo, since we happen to be near 100 degrees, these numbers basically cancel, so whatever we enter for the deadband is what we're going to get. Looks like our peak noise, about 0.35 degrees above and below our set point. So I'll put a 0.4 in for the deadband. Again, we don't have to do any math because our set point happens to be near 100. Don't assume that's the case for your system. Now if we run AutoTune, the noise doesn't trip us up, and we get the 3 closed loop cycles we expect. And if we zoom in a bit, we can see the output didn't change until the noise crossed roughly 0.4 degrees above the set point and roughly 0.4 degrees below the set point, exactly what we asked for. And if we zoom back out and change the set point a couple times, the process variable tracks just like before. Perfect. So using the deadband is another way to avoid noise issues in AutoTune. But you'll want to keep the deadband as small as possible because a large deadband means AutoTune has to wait longer for the threshold crossings, which will result in PID coefficients that are slower to respond to your system changes. Just know you have 2 options when dealing with noise in AutoTune: filtering and deadband. And the best solution might be to use a little bit of both. It all depends on your system and what you're trying to accomplish. Let's turn off the noise, put the deadband back at the default of 0.1, and run AutoTune one more time to get back to our original PID coefficients. Let's get a baseline. I'll change the set point a couple times just so we can see how the normal PID coefficients react. Great. Now, what happens if we double P, the gain? Change the set point a couple times, and we get a little faster response with a little bit of ringing. Exactly what we expect. What if we double P again? The system's oscillating and it can't seem to settle out. Well, that's not good. So what if we cut P to half the original AutoTune value? Move the set point a few times, and we get a much slower response with a larger overshoot because PID couldn't react fast enough. The gain was too low. Again, exactly what we would expect. So how cool is that? Using this process simulator, you can now safely play with adding noise to the signal, with the different PID algorithms, the effect deadband has on filtering noise, changing the coefficients, and all of these other options without having to take your real hardware offline or worrying about damaging your hardware. Then, once you feel confident with this, you can apply that knowledge to your real hardware, run one final AutoTune to tweak things on the real hardware, and you're good to go. Nice. AutoTune on the Do More PLC works really well, but it can only do so much. Things like system noise can have an enormous impact on AutoTune, and if you have an odd system response like this, well, AutoTune may not be able to give you optimum results. In situations like these, it's really helpful to know how to manually tune a PID loop. In the next video, we'll show you a quick, easy, and reliable way to manually tune a PID loop. It uses an open loop tuning method, so we'll also take a look at the Do More's open loop tuning for comparison. Click here to see the other videos in this PID playlist. Click here to learn more about our award-winning tech support options, and click here to subscribe to our YouTube channel so you'll be notified when we publish new videos.